Today, we want to start talking about the next big thing, and that would be integration. Remember that Calc 3 is the easiest of the calculuses because all the thinking is the same. We just need to adapt to functions of more than one variable and then adapt to other ways of describing relationships between variables. So he's spending a lot of time on our derivative business. Now we need to move on to integration business. The other reason that we want to start integration now is because we've all come from different calculus traditions. And so I want you to, I need to talk about the way that I like to think of integration so that it makes more sense later on, the reason for me to say things the way that I say them. Here's how I think of integration. Integration is multiplication, but one of the factors is continuously variable. Integration is multiplication, but one of the factors is continuously variable. Two aspects that we need to focus on. One of the factors is continuously variable. Note that this does not preclude more than one factor from being continuously variable. If 10 students are flunking this class, and I say one of my students is flunking Calc 3, that is still true. So if 10 factors are continuously variable, then one factor is continuously variable. What makes it an integration problem is that one of the factors is continuously variable. Since it's multiplication, but one of the factors is variable, that means we need to drop back to addition. That's what happens when our multiplication, or the factors in our multiplication, become variable. The variable part means we need to step it back to addition. So the variable part says, whoa, we can't do multiplication. Step back to addition. The continuously part is what makes this a calculus problem. So that's the part that's going to have to bring the limits into the situation. Riemann has entered the chat. So in this stepping back to addition part, this is what we do. We think, I want you to think of multiplication as repeated addition. Multiplication is what we get to do when everything is the same. Multiplication is what we get to do we get to use multiplication when the terms are all the same. So if I see the expression 5 plus 5 plus 5, I've got repeated addition. The terms are all the same. I get to use multiplication. Oh, I should This isn't green. Green is where we step back to addition. We get to use multiplication in this case. 5 plus 5 plus 5. We get to say 3 times 5. We get to summarize with multiplication because the 5s, they're all the same. If you were in my class last semester when I was talking about integration and the semester before that, yes, it's always 5, and yes, there's always 3 of them. If the terms are different, then we're stuck in addition. So if the terms are all different, we're stuck with addition. There's no multiplication. So let's draw a graph of how things change. Let's start by drawing a graph with some multiplication. The only multiplication we really need, at least for integration with a single variable, is area is equal to length times width. If we want some other multiplication, distance is equal to rate times time, it's still just product of two things. Length times width, rate times time, work is equal to force times distance. Force is equal to pressure times depth. For functions of a single variable, the only multiplication that we really need is length times width. All those extra applications of integration, they were just all applications of multiplication. Whenever you multiply them, you can turn that into an integration problem. All you need to do is take one of the factors and make it continuously variable. So if our length is constant over the entire width, then we get to use multiplication. Let's say stage 1. Stage 1, the length is constant for all the width. This is just a multiplication problem. I'm going to draw it like a graph. If from 1 to 4, we always see a constant 5, here the length is the same the whole way through. That 5 is our constant length. We get to multiply. No problem. We all got that. Now I'm going to step it up one notch, and I'm going to make my length variable, but not continuously so. I'm going to make different lengths, but they're going to be constant on small pieces. So length is going to be variable, but not continuously variable. This is the green one. So our length is variable, but not continuously variable. There's a place where the length is 3, there's a place where the length is 4, there's a place where the length is 5, but it's all flat across the top. In this case, we get to use multiplication where the length is constant. But we also need to use some addition. So our area is this first box, 3 times 1. The second box is a 4 times 1. And the third box is a 5 times 1. Three instances of length times width. I get to use length times width when our length is constant for the entire width. That's when we get to use multiplication. No problem in this first one. That was just one length times a width. In this second one, we have 3 instances of length times width. Any questions? Of course not, because you've all been through Calc 2. You remember this picture. It's like, oh, I totally remember this picture. Because the next one you're going to draw is the length being continuously variable, and you're just going to bust it back down to this one. You're just going to say, instead of making the length continuously variable, you're just going to flatten it out. You're just going to reduce the resolution on your continuously variable so that you can get just a bunch of rectangles so that you get to use length times width and then just add them up. And then the calculus thing happens. We get a better approximation by increasing the resolution, that is using more rectangles. So how many rectangles should we use? Calculus says use infinitely many rectangles. And then Riemann is like, oh, hell yeah. And then Riemann comes walking in. I high five the ghost of Riemann. And then we move on. But there are other aspects that we want to make sure that we're paying attention to, which is why I'm going all the way back to Calc 2 for this. A lot of things that we want to think about, because we probably remember how to do trigonometric substitution, but we got to remember what that expression is telling us. We know what we're supposed to do when we see a definite integral. But we need to make sure that the thinking behind that definite integral, what that information contains, what that notation contains, so that we can move on, so that we can adapt. We can't just know how to do these Calc 2 problems. That'll just keep us weak. So the third stage, of course, I'm just going to make the length continuously variable. So here, the length is continuously variable. It's not taking steps, it's just moving from whatever it is down here, f of 1 up to f of 3. Oh, it says it right up here, continuously variable. Because I've got that continuous function telling me what the length is. How's everybody okay? Everybody remember this progression? Our strategy when we're faced with this continuously variable length is to say, well, let's just drop this back down to addition. Let's take out the continuous part and drop it back down to discretely variable. So our strategy that looks like 2 O's, continuously. And I'm not going to be able to read it other than continuous. Drop the continuously. down to discrete. It's a math class, I can't be writing doom. Our strategy is to drop from the continuously variable case back to the discretely variable case. And then take the limit as number of rectangles goes to infinity. So drop our continuously variable down to discretely variable, then use infinitely many rectangles. That's the thinking that goes along with our integration process. We want to do length times width, but the stupid length is continuously variable. So we drop it back down to a case where we can use multiplication by making the length constant for little rectangles. Then we can use multiplication, length times width, just like we want. And then we add them up because they're all different, so we have to add them up. So we're taking our multiplication, turning it into a sum. That's all multiplication is trying to do anyway, just add stuff up. Then calculus happens and says we have to increase the resolution from finite to infinite. We have to cross the boundary between the discrete pixelated case and the nice continuous one. And now all of our computer screens are like saying, but I can't do that. I can only display pixels. And then you're like, well, it's okay, computer. You can display an awful lot of pixels and we can't tell the difference because our eyes suck. And the computer's like, oh, yes, that is how we will take over the world. I don't think that's part of the plan. But you know what I mean? The computer can't do anything but this. It's just a bunch of dots. And it fools us into thinking that it's making nice curvy lines. The computer's like, oh, look at the nice circle I made. And they're like, oh, yes, that's a nice circle. And meanwhile, the computer's like, oh, that dumbass doesn't know it's just a bunch of boxes. I can't make a circle. You know what I mean? So this is where we end up with Riemann. Riemann says, just evaluate the function at some point to make the length. This f at xi, that's our length. We get the length by evaluating the function. Then we multiply the length by the width, some small change in x. Length times width, that's going to give us an area. So we're making the function constant for some small change delta x. So length times width, this is where we get the area. Then we just say, do this a bunch of times. Let's say n times. And add them up. Add up the areas of those n rectangles. Then calculus comes in with its big idea. It says, well, it gets better the more rectangles you use, so use infinitely many rectangles. It comes down to us assuming that the length is constant for some small changes. That's making the rectangles. We start by assuming that the length is constant by just evaluating the function. And that's all the parts of our Riemann sum. Any questions? Now we know where this goes next. This is the part that we never wrote down. We'll never write down the Riemann sum. We just use the Riemann sum to get at the definite integral. So this f of xi times delta x, that's our discrete Riemann sum, even with an infinite number of rectangles. Or even with a lot of rectangles. When the number of rectangles goes to infinity, that's when that f at xi delta x becomes f at x dx. So we can think about those two parts going together. We don't really need the dx, but it's so convenient to just say it's like length times width. That's what I base this whole thing on. But I'm fully aware that it's like, well, you can kind of like get rid of that part. But most of you don't know that yet. And you won't find it out until you're long gone from here. And you don't even remember my name. It's like, oh, that calc teacher, he lied to us. We don't need that D part there. Oh, what was his name again? I'll be completely forgotten, so it'll be okay. You won't know who to find. It's awesome, the way I get away with things. But we know that the Riemann sum takes us to the definite integral. Where all that lead up completely changes to this integral from a to b. The f at xi, that's where we're assuming it's constant. We're just assigning a bunch of values. That becomes the continuously variable f of x. And the delta x is our infinitely thin width, dx. So now we've got our continuously variable length and our infinitely thin width. The big transformation happened in the limit as n goes to infinity of the sum as I goes from 1 to n. Instead of plugging in some index that just labels all of the rectangles, we can't have that anymore because we've gone from discrete, where we can number everything, to a continuum. And we just summarize by saying plug these values from a to b into this expression. So that's the big transformation that happens here. When we add up the areas of the rectangles and use infinite rectangles, these are all the values of x we're plugging into this expression. So now this part is telling you the values of x This integral from A to B part is saying plug these numbers into this expression. And at first we're like, oh, dude, that seems like a lot of work. There's an uncountable infinity of values between A and B that I have to plug into the expression. And the fundamental theorem of calculus comes along and says, don't worry, you could just plug the endpoints into the antiderivative. And then we're like, oh, yay, I'm going to forget all of this buildup, find an antiderivative and plug in the endpoints. Woo! So usually when we talk about the fundamental theorem of calculus, we say, hey, don't worry. I know it's an uncountable infinity of things you got to plug in, but the fundamental theorem of calculus has got your back, and you can just do this calculation. And at this point, you need to be like, oh, thanks, fundamental theorem of calculus. And then the fundamental theorem of calculus is like, oh, hey, no problem. All you have to do is find an antiderivative. Then you start learning to find antiderivatives, and you're like, oh, this kind of sucks. And the fundamental theorem of calculus is running out the door saying, too late, suckers. Enjoy your trigonometric substitution. At which point, your Texas Instruments calculator comes in and says, like, oh, heard you having some problems with some antiderivatives. I got a way around that. Maybe you could just calculate these mechanically. Shh, come on, man, cool it. You don't want the fundamental theorem to hear. It's all about this whole find the antiderivative. But what if I told you? Which is great, because the second part of the fundamental theorem of calculus tells you that you can just construct an antiderivative using the definite integral, which is just area. So meanwhile, while you think you're getting away with something, finding these antiderivatives, the fundamental theorem of calculus, the second half, knows already. It's like, oh, they're just going to calculate the area. You know what I mean? I'm wondering if that's why they split the fundamental theorem of calculus. Because a lot of times I'll see the first part of the fundamental theorem of calculus in Calc 1. And then they bring in the second part of the fundamental theorem of calculus for season 2, Calc 2. And so something that you thought was really cool in the first season kind of gets overwritten by the big bad of the second season. You know what I mean? I go, oh, that first season kind of, sometimes it comes out very clumsy. Like, I don't know if you've seen all the Aliens movies, but like go from Aliens 2 to Aliens 3, like the end of Aliens 2. Think about how awesome that felt. Victory. And then at the beginning of Aliens 3, it's like, well, hey, remember Aliens 2? You're like, oh yeah, that was so awesome. Yeah, fuck you. They all dead now. Oh, that kind of sucks. Just kind of overwrite the whole first movie. You know what I mean? It's terrible. What are we talking about? Oh yeah, the fundamental theorem of calculus. It doesn't actually have feelings. Neither does your Texas Instruments calculator. Unless you got the TI-84 AI version. I wouldn't worry about a Texas Instruments artificial intelligence, because I've seen how long it takes that thing to just like graph two curves at the same time. It's like, have it graph three things in simultaneous mode. It's like all boop, 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 boop. It just takes forever. So even if it does get like a robot body and the ability and the motivation to take over the world, it would take it so long just to process all that information that it's not really a problem. You know what I mean? Now your iPhone, that's an opinion entirely. So Here's the structure that I wanted to get at, and the reason I said all this stuff is this integral part is telling you the values that you're supposed to plug into this expression. It's saying plug this stuff into this expression, evaluate this expression at all these x values. The reason that we need to understand how that works is that these expressions are going to change. I'm going to trade my function of x for a function of x and y. That's the first place that we're going to look. We're going to interpret it very similarly. We're going to use length times width, but we're going to add a third dimension. We're going to have length times width times height. Our function is going to be the height above an xy point on the floor. And so what we're going to need over here in the integral part is what points from the floor do we plug into the height times dx? Dx is not going to work. It's going to have a dx and a dy. We'll call it a little chunk of area, a dA. And that dA is going to be a dx times a dy, which means we're going to have a function of x and y, which means we're going to need a bunch of points, a bunch of x's and a bunch of y's to plug into the expression. So we're doing the same thing. Here, our function is telling us a height above some area. And so when I multiply those two things together, we get a volume. The integral over R part is all the points in a region, a bunch of values of x and y. R is some region in the xy plane, and we're going to take all the points from that region, plug them into the expression. We're just going to evaluate the volume at all those points. And so we're doing the same thing. There's just more of it. Any questions? TLDR, we're evaluating this expression at all these points. So that when we increase things by one dimension, we're evaluating this expression at all these points. Now, I haven't told you what the fundamental theorem of calculus looks like here. Doesn't matter. You already know. You take partial derivatives, right? This is just going to go the other direction. If we can sort this out properly, then it's just going to work the same thing we did backwards. Any questions? Comments? Deep thoughts? All right, that's it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.